1, 2.
Hi there! Creator is ETH Zürich's first ever Rover association. We bring together 70 passionate engineering and science students to push the limits of student-made space robotics. Since October 2025, we've built the entire project completely from scratch. From the organization itself to a Rover TERBY and our ambitious autonomous drone JEZERO for the European Rover Challenge. To make a project of this scale possible, we're organized into many sub-teams. While project management drives the overall mission and coordination, our system architects ensure that every subsystem integrates smoothly into a functioning robotic platform. What defines Creator is a shared vision, developing technologies that could one day contribute to the future of planetary exploration.
The Rover is developed by 6 technical teams. The robotic platform builds the chassis, power system and onboard computer. The powertrain team handles suspension and steering. The robotic arm team develops the manipulator and anti-factor. And the drill and astrobio teams design tools for subsurface and liquid sampling while also supporting the scientific objectives. Our navigation and controls team enables autonomous operation through simulation, localization and obstacle detection. Finally, our drone team develops a custom aerial system with its own dedicated hardware and autonomous software stack. We want to take part in the European Rover Challenge because it is one of the closest experiences to a real Mars mission available to students. It's not just a competition, but a rare opportunity to learn how exploration missions are designed and executed.
TERBY uses 4-wheel independent steering to achieve a high level of maneuverability in challenging terrain. Steering actuation is achieved via motors coupled to a 2-stage reduction drive. In addition, the integrated encoders enable closed-loop angular positioning, ensuring precise trajectory tracking and system rigidity under varying operational resistances. Our traction system features a hub motor in each drive unit. The torque transmission was designed to allow TERBY to maintain a top speed of 1 meter per second, even on steep, rocky inclines of up to 35 degrees. Finally, we have our 3D printed wheels. By combining a stiff nylon rim with a compliant hollow TPU tire, we created a mechanism that naturally damps vibrations and maximizes traction where traditional wheels would slip.
The suspension system is the critical interface between the rover and the challenging Mars yard. Built from aluminum, the suspension system is the structural glue of the rover. It connects the main axis, which holds the chassis, to the steering units and wheels. The suspension arms are synchronized via linkages and spherical ball joints. This ensures zero backlash and forces the chassis to average the pitch of both sides, allowing you to turn forwards, backwards, left and right and handle challenges like slopes.
To guarantee safe operation, we integrated a prominent and well-accessible emergency stop button that instantly kills power while keeping the software systems active. The foundation of TERBY is an octagonal frame custom manufactured from modular aluminium profiles. The arm and drill mount directly to this frame, with the drill interface also housing our status indicator light and navigation camera. To prevent overheating, a thermal management system consisting of dual intake and exhaust fans provides steady cross-ventilation for the electronics. Our power rail provides an unregulated 24-volt line and a regulated 12-volt line dedicated to the control electronics. It interfaces directly with our custom battery drawer, which is designed for quick swapping during missions. A key feature of this architecture is the uninterruptible power supply. Even if the main battery is disconnected, the logic systems and communication continue to run.
Our autonomous navigation stack runs on a single OCTI S2, packing stereo depth, an IMU, and Aruco tag detection all in one unit. At its core, a custom factor graph localization system fuses visual inertial odometry with Aruco detections for global pose corrections, while wheel encoders help suppress drift at standstill. Stereo depth gives the rover real-time awareness of its surroundings by updating a local cost map for obstacle avoidance. This cost map is fed into an A-Star planner, and a DWB controller provides velocity commands for the rover's 4-wheel independent steering system. A custom gazebo simulation environment allows for end-to-end validation and development.
JEZERO is a quadcopter built around a custom multi-layer frame. It uses 4 inverted motors, each with an air intake above it. These intakes channel turbulent airflow into the main body to cool the internal electronics during flight. Electrically, JEZERO uses a dual battery system. On the software side, JEZERO runs Aruko detection, pose estimation, and computer vision nodes. Together with a high-level planner node in MATLAB, they allow the drone to navigate the circular perimeter, detect objects, and send precise locations back to the ground station. JEZERO also includes safety procedures that activate if telemetry is lost for too long or if the controller connection is severed. For communication, JEZERO uses 3 links: analog video, telemetry, and control. The ground station lets us view critical telemetry data and initiate missions, while the handheld controller allows manual takeover. Both the ground station and controller can trigger emergency landing routines.
TERBY features a 6 degree of freedom robotic arm designed to handle the variety of tasks encountered during the European Rover Challenge. It has an effective reach of 90 centimeters, enabling probe and sample collection as well as interaction with the maintenance panel. The arm is designed to handle a 1.5 kilogram payload at the end effector. Joint 1 to 4 are driven through pulley transmissions, enabling compact integration. The base slewing ring bearing transfers high loads directly into the chassis. The wrist movement, joint 5 and 6, is realized through a differential gear mechanism actuated by 2 motors located in the elbow. High-resolution absolute encoders on every joint ensure precise task space control. The structure combines carbon fiber, aluminium, and lightweight distal components.
To perform the ERC tasks as effectively as possible, we designed custom fingers for each task. For the maintenance panel manipulation, the fingers have flat contact surfaces with added padding. This improves grip and stability, allowing us to reliably operate control elements. For the probing task, we designed form-fitted fingers that can pick up the probe no matter how it's oriented. The third pair of fingers is designed for surface sampling. They have a shovel-like shape for the collection of regolith. Small integrated teeth help to grip rock samples securely so they don't slip during handling.
TERBY's drilling system consists of 2 main parts, the drill itself and a sample container. For the drill, we use a 70 cm long ground auger with a diameter of 30 mm. It sits inside a carbon tube so the sand doesn't fall out while drilling. The drill is powered by a motor and a gearbox and rotates while being pushed down by a spindle-driven linear unit. While drilling, the auger transports the sand upward in the tube, and once the target depth is reached, the drill is pulled back up. The second part is the sample container. It moves out on a linear rail and sits underneath the drill. The drill rotation is then reversed so that the collected sand falls into the sample container. Finally, the sample container is retracted and safely stored under the chassis.
The astrobiology system consists of a water-based measuring and storing system placed in a closed box to minimize sensor damage and measuring errors. A peristaltic pump pumps water through a flow sensor and a micro-pH electrode into a medical-grade fluid bag. The system includes a TENSI 4.1, which regulates the sensors and pump and communicates with the rest of the rover via CAN bus. The measurements can be started and stopped via the ground station, and incoming data is managed by the TENSI. The sensor accuracy is 5% for the flow sensor and 0.02 for the pH electrode, combining scientific precision and robust design.